Oh my god. All right. And okay, cool. So I'm only like 3 minutes behind schedule. I'm getting faster. This morning, that's too many Ryan Coopers. We only need one. And even one is questionable. I don't know, depends on who you are. So, you're here, we made it. It's the first step. I'm Professor Ryan Cooper. Right now what we're doing is watching a live stream of my laptop. Part of that is just so we have like a record of kind of what's going on. And if you can't make it to class, you can watch. Oh yeah, I like to cover myself with the chat. So then if you see something coming up on the chat, it's like, hey, somebody's trying to ask a question, let me know. Sometimes it's hard to manage both. So I stream all the lectures throughout the semester. You can get to them on this YouTube channel link right down here. And that'll just bring you into the YouTube channel, watching the YouTube channel. So it's turtles all the way down, just a recursive loop. And also, so this main website, this is the only thing on Husky CT so far. It's just this link to my website, and I did that on purpose to just like, we're just getting started. This is just how to find me and how to find like course website. So I just wanted to give a quick tour here to start. Sound good? Cool. And Calendly is like office hours, so you can find like half-hour blocks. Usually it's in sync with my calendar. Sometimes there's weird things that come up of like, oh, I didn't have my kid's dentist appointment on my calendar. Sorry, I have to cancel our meeting. So hopefully we can give each other the grace that we need to get through this hectic, crazy world. Okay. And I should have started with this, of like what class we're in, because then you could have said like, you're in the wrong classroom, like classic nutty professor showing up in the wrong place at the wrong time. Maybe right time, wrong place. Also, I'm late, so it's the wrong place, wrong time. But anyway, applied dynamics. Is everyone here for that class? Good so far? All right, we made it. We're in the right place at the right time. This is a good start to the semester. 90% of life is just show up. The rest of the 10%, you'll figure it out. Like show up, make it, like just be there, add your voice, and things will work out from there. All right, so we're here in Applied Mechanics 2, and let's start off, rather than me telling you more about the class, let's answer two questions. One is, what is this class? And the second one is, well, there's a caveat, there's an asterisk to this question, but the second one is, why are we here? The asterisk is, I know it's required, but why would it be required? Or how would it help you as a requirement? So that's kind of where we're trying to go with this. Do I have a text editor? I just had to change. Okay. I'll find something. LibreOffice. Discard. Just went like simple. Just trying to get to, there we go. All right, so turn to a neighbor, ask them, what is this class? Why are you here, or why is it important? Either one sort of. I mean, you could get real deep of like, why do I exist in this classroom, but somehow. Okay, so here's what I had so far from just, I don't check in with everybody, but at least get a few voices, and then you can disagree or agree, at least get something. So what is this class? It's like energy of motion, or moving parts, like things moving. So then I asked like a few people, like, so then why would you be here? Like why not just build things that don't move, and then problem solved? Now you just have one less thing to worry about in your life. So roughly, I summarize like badly that people are like, well, motion's important. Like, okay, that's fine. Motion is important. Motion's cool. It's like all the fun stuff. It's like moving. I don't know. Other stuff is also cool that doesn't move. But what else came up as you were talking to other people? Anything else? Yeah.
How motion interacts.
Ooh, interaction of motion? What does it interact with?
Really
Anything?
Stationary.
Would it interact with stationary? Like, let's say we have, like a good example, a bridge, very static. Is a bridge holding static items on it? All moving items. So how does the motion of the things going over the bridge affect the static bridge? What is that motion? Like, how is that connected? Anyone, any like quick guesses? Like I'm not asking for like a derivation. This is just like ballpark. Is there a connection? Like, is it quantum mechanics? Could be stress. It could change the stress in it. Is it quantum mechanics? Is it a statistical uncertainty? Is it what was it? What was the bridge in Thor? What was that one called? The Bose-Einstein condensate? Is it one of those that it creates a bridge to a parallel universe where motion and emotion are two opposing deities that have to fight for survival, and yin and yang. F equals ma, right? If you A, you F. If you have A, you must be creating F. So if something's accelerating over your bridge, there's got to be an F that created that acceleration, and your bridge is the only thing there that could have done that. So that's like, just like big picture idea. It's like, even if something is standing still, it still has to deal with moving things. And those moving things, if they're moving, if they're changing their motion at all, they're A-ing, so they're F-ing. I know, it's on YouTube too. You can like rewind, that's not good. Okay, so then motion is important. Interaction of motion on, I'm gonna say like, with energy, forces, what else would motion interact with? Forces, energy, what other things? I don't know, you can think about it. Motion is important. Any other ideas of like why we're here? Like why that might be the case? Or you all like just with your whole heart, your whole life, you've just thought motion is important. And that's what brought you to this classroom today. Yeah? Okay, then this will be easy. All of our motivation is like deep within our characters already. Now we just need to embark on the journey. No arguments? I would rather an argument, but that's okay. Okay, yes.
Because in some way or another it's involved in pretty much every engineering field?
It's always going to, in aero engineering?
No, I would say in almost every engineering field. In some way you're going to have to think about motion.
Yeah, so motion is always going to be like some part of almost every engineering field. So yeah, what would be one where it's not applicable? That's a good question. Where motion doesn't. Computers? What? You got to flip zeros and ones. You're moving electrons constantly. I mean, maybe you want to deal with like a different type of F equals ma. No, I'm not. So, and then also like the packaging of computers. There's a lot of like vibrations that you have to deal with. Sorry, that was very dismissive, but it was a great idea. And I didn't mean to come, I caught myself off guard with how dismissive I was of that. But that is a great, like designing how a computer works, like the theoretical computer science of it. You could do that without F equals ma, right? But then whenever you build the computer, you very much need, like, what is this computer gonna do? Sorry. And then, was there another example? Or computers in the back? Is there? Yeah. It's hard to think of something that doesn't move and that doesn't like touch something that moves. Almost all engineering. But I'm going to say, except computer science design. Let's go computer science design. So if you're doing pure computer science where it's all math, then you don't have to worry about motion because it's all just the ideas of like, how do I make a computer do math for me? And let's go. All right, so let's do a tour. So the class is all about kind of like motions and forces and those kind of things. So a quick broad tour of where we're going with that is like module 1 hopefully is a lot of review where we're just kind of like saying what are the tools that we need to do this course. Like we need Newton's laws, we need definitions for motion, like how do we actually describe motion, how do we define motion, how do we measure it or predict it, and then if you read, and I'm sure over your summer, like your summer reading was just like sitting down and like, I can't wait to read this new edition of Engineering Dynamics and read from cover to cover. So if you did that, this is a little like wacky amount of order compared to your summer reading challenge, because usually constrained dynamic motion, where you're looking at like moving parts and constraints on motion, is like the last thing you do in the semester. But I think it's the coolest and newest part of dynamics, and it's all geometry based, so we do that right up front. So we'll spend some time figuring out what we need to use in the class, and then we'll actually apply it to like some moving parts. So like what are different types of constraint? What is a constraint? How do we use constraints, and like how does that change? Yeah, like this is, like if you're thinking about like moving parts like this, it's only like a 1 degree of freedom system, but lots of different moving parts that are all constrained together. And I know we're using YouTube to watch YouTube, but. And then from there, we'll look at like constrained engineering systems. So go back into like F equals ma, how do we predict motion based on constrained motion? And then looking at like angular momentum and angular momentum, energy, and then also like linear momentum, how we can use those as different tools. And then module 5, the main goal there is pick something that you want to work on. Like it could be an application, like if you have an interest in like doing an internship for a certain company, this would be a great place to say like, all right, what does that company do? What are the main forces involved in either main forces or main like geometric constraints? Like how could I create a little problem in that? So you'll build your own like dynamics project there. And this is open-ended to the point where you can choose any kind of final format you want for it. Every semester I offer interpretive dance as a final submission. I have yet to have an interpretive dance submission, but I feel like the motion of interpretive dance, explaining the physics of motion, has a lot of depth to it. It's just I haven't seen it yet, so I don't know exactly. And I'm not an interpretive dance, I don't even know how to rate interpretive dance, so I'm not really sure where to get started on that project. But other examples would be like a PowerPoint or a report, but something where you dug into what are the physics involved, what's moving, why is it moving, what do I want to move, how do I prevent motion in other ways. So the main goal here for the course is, if you get an A in the course, that's great. Lots of people can get an A in the course, but every individual should have like some kind of story that they left the course with. Of like, so one example is, let's go pop in. I'm just scrolling down. Yeah, here we go. Carolyn took data on her phone of walking, and she wanted to understand how walking affects your knee, and in particular, like a prosthetic knee. Like if you're designing a prosthetic knee, what are forces that you need to design for? So she took some data and tried to, then if you have A and you know M, now you know F, So now you can figure out like what are the forces acting on a knee, and that same knee, whether it's prosthetic or the original, they need to support the same forces. So this is a great question where someone's like, okay, you took dynamics, you got an A, what can you tell me about the course? Now Carolyn can say, well, in the last couple of weeks of the course, I was really interested in how motion affects the knee. The knee is one of the main drivers for kind of walking around. It moves the most of the joints in walking. And when designing a prosthetic, I wanted to understand how the motion of walking affects the actual forces on the knee. I took some accelerometer data. I found the average force is this, the max force is that. Like, she has some real like numbers to back up this little anecdote from the class. So that's my main goal. There's no final, there's no midterm. My main goal is like, you have a story to tell at the end. And it's okay if you don't. I know that's like, sometimes you're just like, I'm just trying to get through this class, dude. I'm like, that's all right. We can work on this however you want. And it could also just be like a fun side hobby. Like someone else was, they couldn't stop playing. It wasn't maybe it was Breath of the Wild. What's the newest Zelda is Tears of the Kingdom. He was playing Breath of the Wild, and he was concerned with the physics of the gliding mechanics. So he went and timed himself jumping off of different objects, timed and measured distance, like how far he went in the game, and figured out what the apparent coefficient of lift and the apparent drag on Link. Zelda's not flying anywhere. Zelda is in trouble. We're trying to help her. And that was really cool too, because it's like it's not a hard thing. Like you could probably figure it out right now, but just taking something that you're interested in, turn that into a project. So that's the main, and in a mile-high view, is define some stuff, apply them to some things that I think are cool, and then you apply it to something that you think is cool. Dynamics is so broad, and that's one of the reasons why it's hard to think of something that doesn't use dynamics is that it's just such a broad topic. Like if you're doing finite elements, the first step is always dynamic analysis. And when I say dynamic, I mean like the motion, like how are things going to move when you apply forces? Like what are the kinematics involved? If you're doing fluid mechanics, it's all dynamics. That one is all F equals ma. I mean, you divide through by the meter cubed, so you end up with like mass per volume and like all of that and different equations. But it branches off into all these different areas. And then even like electrons, neutrons, protons, like all of those follow Newton's laws. As long as you're not moving like, I think by the time you get to 90% of the speed of light, then you need to start considering relativity. But 90% is still pretty darn fast, so you can use it pretty well. Or so there's 4 criteria. One is if you are the size, if you have as much mass as like a black hole, then you're starting to deal with general relativity. If you are dealing with time spans that are like eons, like billions of years, then also you need to deal with some other physics. Like it's not just F equals ma. And then if you're super small, like to the point where you are smaller than an electron, now you need to deal with quantum mechanics. And then speed of light is the last one. If you're like about 90% of the speed of light, now you need to deal with the fact that your mass is changing because you're moving so fast. But everything else, that's a lot of ground to cover. Like a proton that's vibrating, that's F equals ma. So even like protein folding simulations, all of that is just standard F equals ma dynamics. There's no quantum mechanics, there's no relativity, nothing like that. And that's for like drug discovery kind of work, really tiny. All right, so there's a couple of definitions here. We're applying kinematics and we're applying kinetics. And there's some examples here. So what is, ask again, like talk to a neighbor, what's the difference between kinetics and kinematics? Why do we learn both? And why, what are they? What's kinematics versus kinetics? Let me bump this over. Okay. So here, just again, like quick, like snippet of what I had heard, kind of what we were talking about. So like one thing that comes up. One thing that comes up whenever I ask this question is people remember kinematic equations, because for probably a year you were constantly asked to use kinematic equations to do something. What are kinematic equations, like, again, like mile high, what are the kinematic equations describing? What is it? Sorry? Motion? Motion, okay. Motion? Displacement, okay. Displacement, motion. So yeah.
Velocity and acceleration.
Velocity, acceleration. So your kinematics are, so I'm gonna just add to this because you're all like, you all have a good idea of it. Just kind of formalize, all I'm doing here is like taking your ideas and kind of formalizing it. Geometry of motion. So it's specifically like, how do I describe a moving thing with geometry? That's the kinematics part of, so whenever I say like, the position is x of t and y of t, intrinsically I'm saying like, position is a vector. And if it's a vector, then I can do vector math on it, and I can start changing things that way. And if that's a vector, and f equals ma, that means that f has to be a vector. So now I can do f, like vector things on forces too. So you're describing, and sometimes we kind of skip over this part because we jump right into like, acceleration is constant, apply these equations, get the answer. But on a high level, you've made some choices already of like, I have a Cartesian coordinate system. I can describe the position with an x and a y. The x is going to change by this amount, y will do this. So it's your definitions of that geometry of motion. So define position, velocity, all right, so then kinetics, forces and then energy. Is that it?
Will it also include the amount something moves?
The amount that it moves? So if you're talking about like how far something goes, then you're still describing like some kind of definition, like maybe you're measuring your defined change in position or something like that. Forces and energy. And one idea here was like you could use kinematics to find kinetics of like, okay, here's the geometry of what happens. So that means my forces are, ta-da, like big reveal. Would that work? Maybe. It can work, yeah. That's a process called like forward kinematics, where you know, whatever, I have a rocket in space and I know I'm going to apply 100 newtons of force to this rocket. So then its acceleration has to be something. But I could also have the opposite question of like, I don't want this rocket to leave orbit. So what forces do I need what forces do I need to have on this rocket? Like, where does it need to be? How fast does it need to be going? So kinetics. what's like the thing that connects forces and energy? And I feel like energy is a weird, because energy is like kinetic energy, right? Kinetic or potential, which is all based on velocity and position. So can I change this to like work? Instead of work, and instead of energy, call it work? Is that okay? It's okay? Okay. All right. It's okay if you don't think that's okay. You'd be like, what are you, nuts? Work is not energy. What's the connecting thing between like force and work? Yeah.
Work is like the accumulation of force over a distance.
Over a distance, right? Yeah, so the amount of force through a distance is work. So one way, at least that I like to think about, like difference between kinetics and kinematics is kinematics is just definitions for like, what do I see? What kind of motion am I allowing to happen in this sort of hypothetical calculation? Or even if I'm watching something happen, like how do I describe what's happening? Versus kinetics, this is sort of like the cause of motion. What are the forces that were involved in order for this to happen? What were the, and even like constraint, you might have like kinematic constraints. Every time you add a constraint to motion, you're creating some kind of reaction force. Like there's some force creating that constraint. So that's why I think of it as kind of like the causes of motion, whether you think of it as work or a force or an impulse. Do you know what an impulse is? Sudden? Yeah. Sudden. What was it? Momentum? Yeah, so impulse is momentum. Yeah, so if you have, so baseball bat hitting a baseball, you apply to force, it was just really big for a really short amount of time, and it instantly changed momentum. So it's hard to measure that force over a small period of time. So look at changes in momentum, and that would get you there too. How are we doing? We still have like 5 minutes. All right, so then let's do, all right, so we'll get into a little bit of the, actually we'll go back into here. So general kind of structure of the class, you know, everybody's favorite part is like, I can't wait to talk logistics of this course and how I can maximize, optimize my time spent versus actual learning. But 20% of the course grade is participation. That one I leave as a self-assessment. So halfway through the semester, I'll send a form out where you give yourself a grade. You can be as honest or dishonest with yourself as you want. I prefer like just being honest. If you feel disconnected from the class, like you're not really connecting with me or other people in the class, like just say that, and that's totally fine. Hopefully there's some way that you can like kind of give yourself credit for the work that you are doing, or maybe you didn't realize like how many people you were reaching out to. But the main thing is like you're creating some kind of, you're going to give yourself a participation grade with some kind of connection of like, I had a study group, or it could be a combination of things. Like I was in 90% of the lectures, anything I missed, I watched the YouTube videos, and I was always working with 4 other people on these homework assignments or projects or quizzes and things. And so that's an A. Or maybe like you have an internship and like you can't get here, so maybe you had to be a little bit more resourceful of like, I had to reach out to the other section. I would go to some of their lectures, but I was always talking to people in our section to try to like maintain a learning community for myself. And either way is fine with me. So that one's your participation, that one's self-assessed. Homework, these for the most part we're going to be working on in class, because this is like flipped classroom. And does anyone want me to talk through like what a flipped classroom is? Like the philosophy of flipping a classroom?
Yes.
Yes. Okay. All right. So flipped classroom, general idea is that there's reference material that is readings, videos. Now that I'm thinking about it, some of these videos are broken. I fixed some of them, but anyway, I'll get to that. This is my homework for this week, is like getting the class all put together. But mainly the reading assignments, where I give you chapters and specific. So chapter 1 is pretty short. Chapter 2 is longer, so I give you some equations to look at, some different tutorials, and it's your job to kind of like get through that material. Then when we get to class, we'll pop open homework 1 and start working on homework 1, problem 1, and ask questions along the way as we solve those. So class is mostly kind of working through those homework. I guess it's a misnomer, because now it's really classwork and reading is homework. But
how much time would you recommend we block out before each class to go over the material?
So general kind of the general timing of this will be like as we're finishing and turning in homework 1. So you'll have a due date for like homework 1 is due, let's say 3 weeks from now. And I'll figure that out again. I have homework this week. By the Friday, we'll have the entire course laid out, where every homework, project, and quiz has like a due date on Husky CT. So let's say in 3 weeks, Friday night, homework 1 is due. The reading for homework 1 should be done by that point. So if you want to do it all at the beginning, then that's a good way to be like prepared to ask insightful questions as we're working on homework 1, problem 1. The way I used to study and do homework was I would ignore the reading, do all the homework, and when I was stuck, go do the reading. But I do everything backwards anyway. Maybe it's me, maybe it's something else, a deeper problem of the Professor Cooper type. But that's why I set this up. It's like you can do reading and kind of watch these however it works for your schedule and your kind of process. Some people like to have like all the answers before they start. I don't like that. I like to like play around and see what I can do without help first. And you don't have to do it my way. Oh, and okay, then we'll get to this next time, but we'll have quizzes and projects, and that'll be the bulk of that. But we'll finish up going through the rest of this next time. Thanks a lot.